Welcome to our 12th lectures on fact devices. Today we will continue with our TCR and TCSC thereafter. So, we are continuing in 11 lectures on TCR. So, let us continue with the same point where we have left. So, let us do the little bit of analysis of the harmonics that will be present, and ultimately this is also the issue of the power quality, because even though actually you are when you are changing alpha, essentially you will have a displacement power factor. So, this is alpha. So, you will have a displacement power factor when alpha, that is what it is. So, when alpha is more than 0, so it is a non-sinusoidal, and we can do the Fourier series analysis current waveform of the reactor. The fundamental current will be contaminated with the presence of the harmonics, and we know that due to the half wave symmetry only the odd harmonic are present, and we require to consider the lower order higher strength harmonic, because power system itself is a low pass filter. We do not bother about the higher order harmonic, but lower order harmonic may pose a threat into the power quality. So, for this reason, so for Ln, so nth harmonic will be given by Vm by omega Ln by 4 by pi sin cos alpha into cos n alpha minus n cos alpha into n sin alpha by n into n square minus 1, where this value will be given by 2k plus 1. So, where k can be any harmonics, that is k can be any integer 1, 2, 3, 4, 5, 6, something like that. So, we can also actually eliminate selective harmonics which may pose a threat on it. So, that is also we can play around, we can choose alpha in such a way that particular harmonic may be removed. So, only one harmonic can be removed by it, as we have studied in case of the selective harmonic elimination, when you have actually only one triggering once. Once you got this kind of on and off in a half cycle, then we can eliminate multiple of this kind of harmonics, but we can eliminate only one harmonic here. So, let us see what happened. We shall see the actually demerits of using this TCR and how it will increase the contamination due to the harmonics. The dominant harmonic is definitely k equal to 1, thus it will be the third harmonic, and that strength will be around actually 15% of the fundamental. And thereafter, to reduce this harmonic content, the connections multiplier TCR is used, that we will see in a next slide. So, one way essentially can be delta connections, so that it does not go to the line, it will be restricted and circulating current inside the delta. And there can be another solution, that is called multi-pulse delta connected 3-phase TCR and segmented TCR, all is to basically to suppress the third harmonics, which will have a huge strength on it. So, see that this is the essentially this is the alpha in y x axis is plotted with the delay angle alpha, and this is the strength of the different kind of harmonics here. So, this is basically scale of I1, strength of I1 multiplied by 10. So, we can see that this is the I1, it will be gradually going down. Please recall our expressions in case of the fundamental. So, that will be the same, and third harmonic strength you will see that you will have a optimality just below 30 degree or around 30 degree. and it will be actually the most dominating harmonic. We require to suppress it, and unfortunately you can see within the any angle between 0 to 90 degree it cannot be suppressed. So, thereafter fifth harmonic, you can see that fifth harmonic will have a 0 here. So, you can choose to eliminate fifth harmonic, you can choose the angle of alpha in between 30 to 45 degree if required. So, this is a fifth harmonic will have this kind of pattern. They are at a seventh harmonic, they are at a ninth harmonic, they are at 11 and 13 harmonic. This will be the harmonic spectrum of the TCSCR. So, we require to suppress the third harmonic, that is our main concern in case of the TCR. So, 3-phase system we can put it into the delta. So, this is the delta configuration A, B and C, and this is the delta configuration. In the 3-phase system, 3 single phase thyristor control reactor are used and they are in a delta connection. So, that third harmonic will be restricted and is circulating within this line. Under balance condition, the triplet harmonic, that is third, fifth, third, ninth, 15th and so on, circulating in the delta connection, and TCR does not have into the line, and the reactor are bifurcated in either side of the AC source, and so that actually if the short circuit occurs in one of the thyristors or one of the reactor, then the voltage across the reactor is prevented by this actually the inductor present into the system. For this reason, L by 2 and L by 2 will be splitted in every connection. This is the overall architectures of this delta connected TCR, where the third harmonic has been eliminated in from the line. So, thus what happened? So, we will have a harmonics. So, it will be shifted. Previously harmonic content was 2k plus minus 2k plus 1, and now we will have a 6k plus minus 1. This will be the shift, and for this it is called the 6 pearl TCR, and we will have a harmonic content 6k plus minus 1, that is 5, 7, 11, 13, 17, 19 and so on, and no triplet harmonic. Similarly, if you using the 12 pulse TCR, we will see the structure in next slide. That harmonic spectrum will be improved to 12k plus minus 1. So, instead of having 5, 7, we will have a actually 11, 13, thereafter 23, 25 and so on. So, there is a huge shift of the spectrum, and ultimately we know that the low pass filter for power system essentially a low pass filter, it will eliminate the higher order harmonics very simply. So, by using this harmonics, so these are the harmonics will be removed. So, 5, 7, 17, 19, 29. So, what we will be left with? It is 11, 13, thereafter so on, and we have a drawbacks of the increasing. So, what happen, you know, if you make it a pulse better, you can make it also 24 pulse. So, what happen, the number of switches will be drastically increase and the complexity will be increasing, and so we require to have a optimal solution depending on the power quality requirement or the power quality issues. So, for this reason it will have a drawback and it will increase the cost of the system, because you have to put a lot of thyristors and we require a very complex circuitry to control those thyristors. And though we can find out that actually require to suppress harmonic, then we sometime replace this 12 pulse by 18 pulse, 24 pulse, 48 pulse transformer and so on. So, this is the example of the 12 pulse TCR, and it will be assignment for the actual online student to draw the circuits for the 24 pulse TCR. So, essentially upper part is same and you will have a internal delta and you will have a internal star. So, this you will have a, you have studied the vector group and they will have a dy11 or dy1, some kind of vector group will be operating, and accordingly this and this will cancel out the third harmonic and multiple of the third harmonics, and essentially you are left with the other harmonics. So, this is the configuration of the 12 pulse TCR. Now, what is segmented TCR? So, in order to reduce the harmonic, another method is to segment the TCR, that when you put a parallel path of the TCR. This method is used for the high power application, because you may, once you have a very high power rating, then you require to put the thyristors into the parallel combination. Thus, definitely it makes sense to use this actually the segmented TCR, and each will absorb some amount of the reactive power. So, TCR will absorb the reactive power equal to the total power by M. So, total power will be Q total and one component will be have a M. So, what does it gives? It gives the redundancy. If one of the block it does not working, so it will be M minus 1, ultimately the whole system will work, where M is the number of TCR. Sorry, it will be M, not N. So, therefore, the magnitude of the harmonics will be reduced to the factor of 1 by M for non-functional one, and it is combination of the both, that is TCR and TSR. Only one of the TCR, only one of the M reactor is having a delay angle controlled, and each other remaining M minus reactor only will have a off and on control. So, this control is very easy. One will have a masters where you can change it, and other will have just on off control depending on the total reactive power required. The losses associated with the schemes are generally lower than those characterized by the TCR, because they will be only on and off of other module, except one will have basically a delay angle control, and thus switching losses are reduced here in this configuration. So, this is the case of the segmented TCR. So, one will have the alpha, other just on and off most of the cases. So, other will have a delay angle only alpha equal to 0. So, this is called the segmented TCR. So, what happen, since these will gives rise to all, if it is on, then no third harmonic will be there. Third harmonic will be arising only from this component, others, because this have a alpha control, let us just say, other will have a on off control. So, harmonic source of the harmonic will be generated by this element only of the TCR, other will be actually handling the power accordingly. So, fourth TCR is all is operating thyristor control, all other operating as TCR. So, this is the principle of operation, and total current will be basically I1, I2, I3, I4, and accordingly it will change. So, this is the very simple and effective solution for high power and high current application. So, what happened here? Let us see how TCR works. So, this is the value of L and you have a delay of 90°. So, this is L1, thereafter this is L2, thereafter L3, thereafter L4, and L4 will have a alpha control, you can change the alpha. So, what happened here, you have operated L1 till this point, thereafter it is off, and you have operated L2 till this point, thereafter it is off, similarly L3 and so on. So, thus gradually you can find that your current flowing through these devices get reduced, and it is almost sinusoidal, because only this fourth element will have alpha control, other will not have alpha control. So, for this reason gradually current got damping. So, it can be effectively damped in this way, and thus you can handle the power quality as well as the reactive power demand as required by the devices. So, now let us see the another shunt compensator, that is TSC, thyristor switch capacitor. So, single phase thyristor switch capacitor consists of the capacitor, a bidirectional thyristor valve, and a relatively small surge current of the reactor. So, what happens generally, inductor required to be placed to block the high inrush of the current of the thyristor, and it is generally the capacitors will be switched on and switch off, and thus it will deliver the VAR most of the cases instead of the absorbing VAR, and it will control the reactive power in that fashion. The reactor is needed primarily to limit the surge current, that is what I am saying, and the valve otherwise high current will flow and actually it may damage the thyristor, and thyristor valve, and it may also use to avoid resonance with the system. So, ultimately this will be used as actively damping these devices, because this capacitor and the inductance in the power system may cause resonance, and thus we require to prevent that resonance. For this reason we have placed an inductor into the system. So, under steady state condition, when thyristor's valve is closed, the current is flowing and it is giving a voltage V. So, V should be actually Vm sin omega t by XL plus XC. So, ultimately you get the current equal to V n square n minus 1 omega c, that is nothing but XC into cos omega t, where n is given by the resonance frequency, that is omega square into LC. So, the TCSC branch can be disconnected or switched out at any current 0 by parallelly removing the pulses of the thyristor valve. This is one of the biggest advantage. Let us understand what as I said. This branch can be disconnected or it can put it off any time, because it has a leading power factor at any current 0 by prior removal of the pulses of the thyristor valve. At 0 current crossing, the capacitor voltage is at peak value. So, we have to keep in mind these things. So, capacitor is holding the maximum value when you are actually switching off the thyristors. Thus, what happened? The disconnected capacitors stay charged at this voltage, and you require to find an alternate actually a safety mechanism to discharge the capacitor. So, that is extra effort you require to put it to discharge the capacitor once it is put it off. Consequently, the voltage across the non-conducting thyristor valve varies between 0 and the peak current value at the applied AC voltage, and the voltage across the capacitor will be Vc will be equal to V n square minus 1. So, if n is quite large, this can be neglected. So, V will be equal to Vc. So, what happened when it is switched? So, this is the current where current is almost lagging by 90 degree, and this small value is the inductor voltage. And what happened here? This is the supply voltage, and here you have put it off. So, capacitor will maintain this voltage, and thus switch will be subjected to this oscillation and will have a stress of actually of the TCSC of this voltage value equal to V, if value of n, that is quite logical, will be very high. So, n square minus 1 is almost equal to n. Now, let us consider the case where it was off, and this is the voltage Vc, and it was holding that peak value of the voltage, and it is on. Thus, voltage will be of the Vc will be swinging like this with the supply voltage, and current will be actually will have a swing by 90 degree phase shifted. All of a sudden here you put this thyristor off, you have not triggered. So, then what will happen? Then again it will hold the voltage of minus Vc. And what happened? It was conducting initially, and it was non-conducting initially, but it was holding a minus Vc voltage initially. Then while off, you will find that actually it will hold a positive voltage. So, this kind of feature you will be finding across the capacitor voltage in case of the TSC. If voltage across the disconnected capacitor remains unchanged, the TSC bank could be switched it again without any transient at appropriate peak value of applied to the AC voltage for the positive A and the negative at B when it is charged into the reverse polarity. So, as such there will be no transient when it is switched on. This is one of the advantage of TCSC, that transient phenomena is not been observed in case of the TCSC. So, generally what happen, we should be discharge the capacitor. Normally the capacitor bank is discharged after disconnection. Thus, reconnection of the capacitor may have to be excited some residual capacitor voltage between 0 to some value Vc. To minimize the transient disturbance, if thyristor valve is turned on at those instant at which capacitor reducer voltage and the applied voltage are equal, then we will find no transient, right. If there is a mismatch between the Vc and the applied voltage, then transient will occur. So, that is when the voltage across the thyristor valve is 0. So, at that point we should try to switch on the switches. So, we will not find any transient. So, we are basically switching on where the thyristor voltage is 0. Otherwise, switching transient will be observed. The switching transient is obtained the fully and a partial discharge of the capacitor generally. Unfortunately, it is there. So, this is the first case. We will discuss the fully discharged capacitor. So, what happened? So, this is the Vc and this value is Vi, and once it is partially fully discharged, it has to build some voltage from 0 and thus high current will flow through the capacitor and current will have this kind of profile and it will be stabilized after some cycle. And similarly, assuming that it is partially discharged and this voltage is half of the supply voltage, and then also you will have a peaky current, but this peaky current will be little bit reduced. It was 1.5 times the rated voltage, it will be little more than 1, that means actually 120%, and thus current will be flowing like this, thereafter it will be stabilizing. So, this will be the condition once you turn it on. So, this kind of transient phenomena will come across the picture. We have discussed the transient stability. So, this system is transient, this transient stability will come into the picture. How we will damp out the oscillation of it in DCSC, that is a challenge of the good FACS designer. So, considering those things, we require to see few aspects. These transients are caused by non-zero dB/dt. Please understand that non-zero dB/dt at the instant of the switching. If voltage or current either is 0, there is no problem. If without series reactor would result the instantaneous current value, that is I value should be equal to I equal to C dB/dt of the capacitor. And to limit this current, the limiting, what does it do? This limiting reactor actually limits this current. The limiting reactor will slow down the rate of change of the surge current. For this reason, we have to put a small inductor to actually high rise of the I C dB/dt. The interaction between the capacitor current and the limiting reactor with damping resistance produce the oscillatory transient. And the control system, now we are, this is a domain of research, control system is trying out the damping, actively damping this oscillation. So, thyristor switched capacitors, what are the takeaway? We require to operate at a transient free operation. So, condition for the transient free switching is actually have two simple rules to follow. If the capacitor voltage is lower than the peak voltage, then correct instant of the switching is when instantaneous AC voltage become equal to the capacitor voltage. The moment it will cross, you switch it on. If residual voltage is equal to or higher than the peak voltage of Vc, generally it does not happen, then correct switching peak will be at the minimum position, where thyristor valve will have a minimum voltage. So, we should be switching on at the peak. So, the rate of dB/dt is very low. We have to make dB/dt low, so that the currents, that is the C dB/dt will be low. So, this is the principle of operation. So, we have to reduce the dB/dt. The next, actually what are the takeaway? Thyristor switch capacitor, the maximum possible delay in switching in the capacitor bank is one of the full cycle is applied to the AC voltage. That is the interval of one positive or the negative peak to the next negative peak. So, around in case of the 50 Hz cycle, it should be around the 10 millisecond. For firing delay control, it is not applicable to the capacitor. The capacitor switching must take place at a specific instant in the each cycle, where there will be a condition of the minimum transient, that means where the applied voltage and the capacitor voltage become equal. Generally it happens in the twice in each of the cycle. So, it will be alpha or 180 degree minus alpha. So, we have to see that which where you can conduct. So, each cycle and condition of the minimum transient is satisfied, and for this reason TCSC branch can provide only steps like change in the reactive current and the from maximum to 0. So, you can have a no linear actually ramp on. So, you can have only the steps change in case of the TCSC. So, this is the principle or the features of the TCSC. Okay. So, now let us see the the current in the TCSC branch varies linearly with the applied voltage according to the admittance, and it does not have a much problem with the harmonics also. Maximum applied voltage is corresponding to the current are limited by the rating of the TCSC components, capacitor and the thyristors valve. So, this is basically the IC versus VC. To approximate continuous current variation, several branches of the small TCSC can be placed same way what we have seen actually the segmented TCR. So, Bmax will be given by actually this line. So, tan theta of this line, this is a maximum voltage rating of the capacitor and the thyristors, and this is the current handling capability of the thyristors, and accordingly we can find it out what should be the maximum admittance of the line. So, we shall carry on our next class with another FACS devices of the shunt compensation, namely STATCOM, and thereafter we will compare with the all the 3 FACS devices on the shunt compensation. Thank you for your attentions. We shall continue our lectures on the FACS devices.